Hello everyone and welcome to a presentation. My name is Samuel C. Maina. I'm a researcher at Microsoft Africa Research Institute, and this is some work that I've been working on with my colleagues here at Microsoft. So we're going to be going through some of our findings on this particular topic of evaluation of dependency structure for multivariate weather predictors using Copulas. And the outline of my presentation is going to be as follows. First of all, I'll introduce the problem we're trying to address, and then introduce the theory of Copulas that we'll use in this particular work. And then I'm going to take us briefly through some of the experiments we conducted using different types of Copulas and the findings that we've found. And finally, I'm going to wrap it up with some potential applications that we've seen that can be useful coming out of this work, and also some pointers to the future work. In the global south, the effects of climate change have resulted in more frequent and severe weather events such as drought, floods, and storms, and this has led to crop failure, food insecurity, and job losses. Now, these effects are expected to increase in intensity in the days ahead, which will further disadvantage already marginalized communities and worsen the existing inequalities. Now, the climate system is characterized as a chaotic system due to the interplay of different variables such as solar radiation, temperature, pressure systems, ocean currents, precipitation, and cloud cover. And this poses a significant modeling challenge. So what we need is precise distributional characterization of different weather variables that will lead to the development and assessment of better stochastic models. Now, the state-of-the-art models at the moment involve an ensemble of both numerical weather prediction models and machine learning, and these are proving to be quite reliable in forecasting different timescales. However, accurate weather forecasting remains a challenge, particularly in the sub-seasonal time horizon, despite the advances that we are observing. And this is as a result of this complex interaction of these variables that I've talked about. To be able to provide this precise distributional characterization of these weather variables, we encounter different interesting questions. For example, what would be the joint probability of concurrent or even compound events occurring happening in different countries? We could also ask ourselves, what is the joint distribution or the joint probability of a weather variable, for example, this month and the same variable a few months down the line, or the same or one variable, particular variable this month and another different variable a few months down the line. And so we want to be able to learn realistic joint distributions that will aid us in giving better predictions, or even be able to explain different outcomes or different weather events, and in some cases even be able to discover some hidden curve movements of these weather variables. The Gaussian mixture model is one of the commonly used techniques in analyzing the intricate dependency structures in multivariate datasets, particularly in cluster analysis and density estimation. However, it has limitations such as the requirement for Gaussian dependencies between variables and Gaussian marginal distributions, which unfortunately can yield inaccurate estimates in some cases. And therefore, we end up considering using a different framework for understanding this dependency structure. And in this particular case, we look at the concept of copulas. Now, copulas are defined as probabilistic models that enable us to separate the marginal distribution from the dependency structure of a multivariate distribution. The beauty with these copulas is that they are straightforward. They are a straightforward way of describing the dependency structure in a multivariate setting, and each copula actually represents a distinct dependency structure. Now, we have bivariate copulas, which capture dependency structure between two variables, for example, temperature and precipitation. And then we can actually now have a look at a case of multivariate setting where now we end up having different variables of interest. Now, within a bivariate setting, we have two broad families, the elliptical families of copulas and the Archimedean family of copulas. Now, the elliptical ones have the advantage that they are quite simple, and they exhibit elliptic symmetry. And the good thing about them also is that they're quite easy to interpret. Now, the alternative is the Archimedean family of copulas, and in that case, they are useful for capturing tail dependencies. So examples of elliptical copulas are the Gaussian copula and the student copulas. And the example of these Archimedean copulas are the Clayton copulas, Gamble copula, and the Frank copula. Now, Expanding this to the multivariate setting creates a problem due to increased complexity and difficulty in accurately capturing the broader dependency structure. And therefore, some advanced copulas were developed, and these are what we call the vine copulas that were proposed by Joe and further developed by Bedford and Cook. And the idea is that they represent this dependency structure using graphical representations in what they call the R-vine tree structure. And by construction, these ones are made by pair copula construction, where between each particular variable, instead of assuming the same copula captures everything, for example, the Gaussian copula captures the whole dependence of maybe 28 variables, where for each pair, a unique copula builds up this particular relationship. Now, having looked at the problem statement in terms of what is it that we're trying to do, and also having introduced the tools that we want to use for our work, we now go ahead and show how did we apply this to solve our particular problem. We consider daily data from 3 weather stations in Africa, that is in Nairobi, Cape Town, and Kigali, and these are for a period between January 2021 and December 2022. And we looked at 8 different variables of interest: temperature, wind speed, cloud cover, relative humidity, and pressure. And in our case, we wanted to answer 3 particular questions. 1, are the bivariate relationships within each location linear, or do they have some tail dependencies? Now, the second question we wanted to investigate was, are the bivariate relationships across different locations captured by the same variable? In other words, if you look at, for example, pressure and cloud cover, and then you look at the dependency structure between those 2 variables in one particular station, it's the same copula model capturing this dependency structure in Nairobi, the same, for example, for the same pair in Kigali. And the last question we wanted to answer was, what is the best representation of this dependency structure in high dimensions for each particular location? Before we proceed with the analysis, we actually started by asking ourselves a trivial question. Are these variables Gaussian in the first place? And so we ran a normality test on all these particular weather variables for our different locations, and we did a chi-square goodness of fit test at a confidence level of 5%. And actually what we observed was that out of all these 8 different variables, for example, in Nairobi, we only found that only 2 variables actually come from a Gaussian distribution. For Cape Town, we actually found only 1 particular variable, which is actually the mean relative humidity for a day. And in Kigali, we actually observed it's only the minimum pressure over 24 hours that follows the Gaussian family of distribution. We then did a goodness of fit, or a selection of the best copula fit for each of these particular locations. And in this particular case, we looked at the vine copulas for the high dimension for the 3 particular locations. And we observed that for Kigali and Cape Town, the R-vine copula best captures the high dimensional dependency structure, whereas in Nairobi, the C-vine copula captures this best. So for demonstration purposes, we show on this slide the results of an R-vine copula fit for the Rwandese weather station. And for this work, we use the R-vine copula lib function from R. And what we actually observe is that different pairs have different dependency relationships. And what that means is that we have both elliptical and Archimedean type of families being used to capture these particular relationships. And in addition, we also observe some interesting findings in the sense that we have the presence of rotation for some of the Archimedean copulas. And for example, if a copula is rotated by 180 degrees, we end up having what we call a survival copula, whereas if it's rotated by 80 or 270 degrees, we end up having a model that can actually capture negative dependencies. And the beauty of survival copula is that they can actually be used to model the joint behavior of extreme weather events. And this will allow us to have a better understanding of the dependencies and the likelihood of simulation. So from these results and more results based that can be found in the complete paper, we observed that there is non-Gaussianity in these weather variables, and so it will be important to consider a broader model that covers different dependency structures whenever we are investigating the problem of joint distributions. The other thing we also noticed is that the dependency structure in these pairs exhibits both symmetric and tail dependencies, and with different copulas being the representatives of these different relationships for the different stations of interest. And also, the last observation we made is that the dependency pairs across different locations varies or it changes, and therefore this points to the existence of the spatial impact on the density function for different weather variables, yes, events. We believe that our work can contribute to enhancing the existing weather models, weather prediction models, and in particular, understanding the dependencies at the subseasonal scales or timescales, which are difficult due to the complex dependencies on both on the local weather variables and also at the global weather level. So, for example, given a prediction of a certain weather pattern, so for example, an El Nino event, a copula function can actually inform how this particular ocean pattern affects maybe temperature, precipitation, or even something like cloud cover at a certain maybe inline observation station. And so we believe that this work has potential extensions that can be in modeling the dependency in large data sets, or maybe even in exploring a combination of satellite imagery observation and ground-based measurements. We also believe that these copula functions can actually be used in modeling the joint dependencies on the spatial temporal horizon. And so we believe that this work can contribute to improving the reliability and the predictive power of our forecasting models. So thank you very much for taking time. And at the end of it, I have provided some references that can be useful for further research on this. Thank you.